Okay, good. Here we are. Our last session is about web security. So we have two talks. The first one is by Avinash. He works as a security researcher for White Ops, and he's originally from India. And I guess he will be Q&A live from India. He knows pretty well Italy because he did his PhD in University of Trento. And so down here in Italy, in Trento, there is a research lab focusing on security. So he's been there, and he's also been with Bruno Kassler, a research institute down here in Italy. After that, he moved to France, where he worked for Sub Lab France. We have similarity between myself and himself. I'm not sure Avinash is aware of that, but I also work for SAP Lab France in South France. Sophie Antipoli is close to Nizza. And so, yeah, we can then, offline maybe share some thoughts about this experience with his company in French Riviera. After that, he worked as a researcher, as a postdoc for India with Professor Juan Caballero, good friend of mine. He did a lot in malware research. While Avinash focused exclusively on web, so actually it's the first time that I hear someone working with Juan but doing web instead of malware. So very happy, that that Juan is also looking to other aspects of security apart from malware research. So in this presentation, Avinash, we talk of COSI, COSI, which stands for Cross-Origin State Inference. He came up with this name, and I'm very much supportive of having someone that formalized under a single umbrella a bunch of different attacks that have been present over the last 5 to 6 years, but went with different terms. So now we have a term that indicates a group, a family of attacks, and I'm looking forward maybe to have something or an organization like OWASP that would integrate such new term into their collection of security, web security vulnerabilities. All right, so that's all on my side. I would say sit down, relax, have a coffee, and enjoy the next presentation.
Hello everyone, I am Avinash Sudhodanan. First of all, I would like to thank the organizers of NoHat 2020 for giving me the opportunity to present my research in front of such an amazing, diverse audience. So today I am going to be presenting about cross-origin state inference attacks. So since it's a long name, throughout this presentation I am going to be referring to these types of attacks as COSI attacks. So this is a joint work with Sohail Khodayari from CISPA Saarbrücken and Juan Caballero from IMDEA Software Institute in Madrid. So what is a COSI attack? In a COSI attack, a malicious website infers the state of a user at another website. So let's see an example to further understand this attack. So in this example, there is a user Alice who is playing the role of the victim. Alice has a web browser. So Alice is a security researcher. So Alice gets invites for being the reviewer of security conferences. So here is a conference named FooConf, that is using hotcrp.com for managing its review process. So if any of you are into academic security research, you know that most of the top security conferences now use hotcrp for managing their review process. So same like that, FooConf is actually using hotcrp.com for managing its review process. And Alice is one of the reviewer of this conference. As you can see, Alice has been assigned 2 papers for reviewing, paper number 278 that was unfortunately rejected by Alice, and then paper number 997 which was accepted by Alice. Now let me introduce you Malice, who is playing the role of the attacker. The goal of Malice is to actually check whether Alice is the reviewer of one of the papers. Let's say paper number 278. But FooConf uses an anonymous review system. So the authors will not know who reviewed their papers. And the goal of Malice is to exactly break this anonymity, in the sense that Malice wants to know who reviewed which paper. So in this case, let's say Malice wants to know, let's say Malice was the author of paper number 278. Malice would like to know whether it was Alice who actually reviewed their paper. So in order to perform this attack, Malice first sends an email to Alice saying, pretending to be, let's say, the PC committee chair, saying, "Hi Alice, click here to finalize your reviews of FooConf." So Alice, if Alice thinks that they should click on this link and accidentally clicks on this link, then a malicious website is actually loaded at the web browser of Alice. So this malicious website is actually controlled by Malice, and it is actually through this website that Malice infers whether Alice is actually the reviewers of some of the papers. So the goal of this malicious site is actually to infer across origins, the state of Alice at different websites. So some of you must be thinking, what does it mean by inferring the state at foo.hotcrp.com? So let me explain to you what are these states. So first, let me show a simplified representation of the attack. There is Alice, there is the web browser, and the two websites, foo.hotcrp.com and the malsite.com, which is actually controlled by the attacker. And the mal site's goal is to actually infer the state of Alice at foo.hotcrp.com. So what are the states that can be inferred by malsite.com? The first type of state is the login state. The login state can have two values, logged in state and logged out state. So inferring the login state can be seen as the malsite.com inferring whether Alice is actually logged in at foo.hotcrp.com or logged out of foo.hotcrp.com. So this type of attack, where a website infers the login state of another website, is commonly referred to as login detection attack or login oracle attack. Another type of state inference is the account type state inference. That is the malsite.com inferring whether Alice has a reviewer account at foo.hotcrp.com or whether Alice is simply an author, or if Alice is the admin, let's say the PC chair of foo.hotcrp.com. Another type of state inference is the content ownership state inference. So let's say if Alice is the reviewer of paper 278, then Alice will have ownership over the reviews of paper 278. However, if Alice is not the reviewer of paper 278, then Alice will not have access to the reviews of paper 278. Next state is the account ownership state. So let's say there is a user account with the user ID user217. So from the string user217, it is not clear who actually owns this account. So if malsite wants to know whether Alice is the owner of this account user217, then that type of inference is called the account ownership state inference. So this type of attack, where a malicious party links an online account to a real world identity, that is user217 to Alice, is commonly referred to as de-anonymization attack. So to summarize what we discussed in this slide, in a COSI attack, the attacker's goal is to infer the state of a user at another website. And COSI attacks have been known by different names such as login detection attack, login oracle attack, de-anonymization attack, and whatnot. So in order to understand how COSI attacks can be performed, we need to understand what are state-dependent URLs, because in COSI attacks, state-dependent URLs are leveraged. So what are these state-dependent URLs? So state-dependent URLs are those URLs that return different HTTP responses depending on the requesting browser's state. Let's see an example of a state-dependent URL. So in foo.hotcrp.com, there is a URL that is foo.hotcrp.com/api.php/review p equal to 278. So basically this URL is pointing to the reviews of the paper number 278. So why is this a state-dependent URL? It is a state-dependent URL because if you access this URL from the state where you are logged in at foo.hotcrp.com and you are logged in as a reviewer and you are the reviewer of the paper number 278, then the HTTP response returned will have a status code of 200 and it will return in the response body the reviews of the paper. However, if you are in a state where you are logged in at foo.hotcrp.com and you are a reviewer, but however you are not the reviewer of paper number 278, then an HTTP response code of 403 is returned. So comparing this to our example, let's say if MalSite wants to know whether Alice is the reviewer of paper number 278, then MalSite can actually send a request to this specific state dependent URL pointing to paper number 278, and then the response returned will be either 200, will have the status code of 200 or 403, depending on whether Alice is the reviewer of that paper number 278 or not. However, one thing must be noticed. The domain of malsite.com and foo.hotcrp.com, they are two different sites, so they don't have the same web origin. Because of this difference in the origin, the web browser will not allow malsite.com to directly read the response headers, response code, and the response body. So because of this restriction, MalSite will not be able to directly read the response and infer that Alice is actually the reviewer of paper 278. Because of this restriction, the attacker will have to come up with different ways to know what was the response status code. This is where cross-site leaks comes into play. Cross-site leaks are basically browser side channels for inferring the response of cross-origin responses. There are different types of cross-site leaks discussed in the literature. I have actually listed some of them with their references. Due to lack of time, we won't be able to go through all of them, but we will go through one of them in very detail. So let's go through the events fired cross-site leak. So let me give you a quick background of what are like DOM events or browser events. So this is a bit basic information for people who are like already familiar with web applications, but since we have a diverse audience, I wanted to make sure that everybody understands what I'm saying. So web pages are basically defined using the hypertext markup language, and there are HTML elements that are the building blocks of these HTML pages, and each HTML elements are actually defined using HTML tags. For example, there is the head tag where all the links to the CSS and JavaScript goes, and then there is the body tag, and then there is the script tag, and there are many more tags. And some of these HTML tags can load or include external resources. For instance, here I have actually listed some of the top HTML tags. So these are the tags, and they have some attributes that basically takes as values different URLs. And these URLs are actually pointing to, let's say, if it is a applet HTML tag, which is currently deprecated, it has this code attribute pointing to an applet. So basically these are tags that can be used to include different types of resources. So DOM events can be leveraged to check the status of these resources. So using those special HTML tags, we are actually including different types of resources. So DOM events are a feature that can be leveraged to check whether these resources were loaded correctly or not. Let's see an example. So there is the script tag that has the attribute src, in which you can actually point to a script, JavaScript, and then there are these events on load and on error. So basically what happens is if the loading of this script is success, then the on load event is triggered, and then as a result of that, the success function is executed. If this URL did not return a JavaScript, then the on error event is actually fired, and this will result in the fail function being executed. So why are we discussing about this? It is because in the event fired access leak, the DOM events are basically abused by the attacker. So let's see how this is done. So in the malicious site, the attacker here uses the embed HTML tag and points to the state dependent URL that we discussed earlier, that is pointing to the reviews of paper 278. And then the attacker defines the onload event pointing to the reviewer function and the onError event pointing to the not reviewer function. So what happens when there is an HTML tag defined like this? When the user's browser loads this malsite.com, as a result of this HTML tag, an HTTP request will be sent to this state dependent URL. And if the user is actually logged in as the reviewer of paper 278, then a 200 response code is returned. And as a result of that, the onload event is actually triggered because it was a 200 response. And then the reviewer function is actually executed. So this means Alice is actually the reviewer of the paper 278. Similarly, if Alice was not the reviewer of paper number 278, then a response with code 403 is actually returned, and this will cause the onError event to be triggered and the not reviewer function will be executed. So in this way, malsite.com can know what was the cross-origin response that was received, and then thereby determine whether Alice was the reviewer of paper number 278 or not. This might seem very easy in this example. However, there are different challenges for mounting these types of attacks. So the first challenge is that multiple states can have the same response. So here I just discussed the two states where the user is the reviewer of paper 278 and not the reviewer of paper 278, and they have two different response code. However, what if the user was not even logged in at hotcrp.com? That is, like, the user is logged out of hotcrp.com when the attack is being performed. When this happens, then also a response code with an HTTP response with the status code 200 is returned. As you can see, this is the same as the case where the user is actually the reviewer of the paper. So what might happen is, if the user simply depends on the onload event being fired, if the user is not even a member of foo.hotcrp.com, the attacker might think that they are the reviewer of the paper. So this can lead to false positives. So as I said, the first and the last states will have similar impact, that is the onload event being fired, and lead to false positives. So the second challenge is that different XSS, the same XSS leak payload may work differently in different browsers. So let's see an example. So the example I showed, where the attacker is actually using the embed HTML tag to determine whether the user is whether Alice is a reviewer or not a reviewer, it actually works only in Firefox and Microsoft Edge. It will not work if Alice was using Google Chrome browser. So in order to handle Google Chrome, there is a way. The only difference is that instead of the embed tag, the link tag should be used. This is because different tags and the events fire differently in different browsers. I think this is mainly because of the difference in the underlying browser engines. So in order to perform a cross-site leak attack, in order to perform a COSI attack in a robust way, the attacker has to accommodate for multiple states having the same response and then the same payload behaving differently in different browsers. So in order to make the job of the attacker easy, or in order to help security researchers' job easy, we introduced what is known as COSI attack classes. So what are these attack classes? They have a name and they have the state dependent URL responses that it can differentiate, and then the cross-site leak associated to the attack class, and then the browser support details. So let's see an example. So this is one of the attack class that we defined. It basically has the name event fires status error script. It basically can differentiate between a response with status code 200 and a JavaScript content type, and a response with a status code 4xx or 5xx response. And the XS leak that is used in this attack class is the script HTML tag, and the manifestation of the difference in the response is actually visible through the on load and on error events being fired. And this attack class is basically supported in all the three browsers, because we conducted various experiments on these browsers with this type of setting. So same way, we identified a lot of different attack classes. We conducted a lot of experiments with we tried to cover almost all the HTML tags and cross-origin request sending. So precisely, we identified 40 different attack classes for performing COSI attacks. Out of these 40 attack classes, 21 of them were new attack classes, in the sense that they were not discussed previously in the literature. And as a part of this research, we even identified a completely novel cross-site leak method, a browser side channel leak method. It is actually based on the PostMessage API. So let me quickly explain to you what is this novel cross-site leak method. So in order to understand this, I will have to quickly explain to you what is the PostMessage API. So the PostMessage API allows browser windows to talk to each other, no matter whether they are from the same origin or a different origin. So to give you an example, site1.com can open site2.com in a new window and then exchange messages with it using the PostMessage API. So this cross-site leak that we identified that uses the PostMessage API works in the following way. So it is actually applicable to state-dependent URLs having the following property. So let's say there is a blog website and there is a blog article with the ID 123. So if someone visits this URL that is trying to fetch the admin panel of this blog article, then if they are actually logged in as the owner of this blog article, then an HTTP response containing a post message admin is actually returned in the response. However, if they are not the owner of this article number 123, then a response with a post message error is actually returned. When this happens, let's say there is a controversial blog posted in blog.com with the ID 123, and the malicious party wants to know whether Alice is actually the author of this controversial blog article. What they can do is from Alice web browser, they can actually open a malicious site, and this malicious site can actually open this state dependent URL in a new window. And as I said, if Alice is actually logged in as the owner of this article, so in that case, Alice will have the state owner of article 123 in blog.com. What happens is that the state dependent URL that is in this window there will be the code for sending the post message admin. As I said, this is the response received if the Alice was the owner of the article 123. And what this will cause is that since it's a broadcast post message, this message is actually received by the malicious site. It is a broadcast message, so it is actually received by all the sites which are actually opening it. And since the message is admin, as you can see, the message admin is received on if the state is actually the owner of article 123. So in that way, the malicious site can know that Alice is actually the owner of this controversial article 123 returned by an anonymous user account at blog.com. So yeah, this is basically the code to check whether if it's the admin message received, then it's like the state is that it is the owner of the article. So there are actually a lot of related work done when it comes to COSI attacks. However, there are some limitations. So it is a bit messy in the sense that different people call these attacks different names like login detection, login oracle, URL status identification, etc. And there is not much discussion on the need to handle these overlapping states and then the support for multiple browsers, that is the same attack payload working differently on different browsers and all this. And then there is also not much discussion on automatic detection of COSI attacks and the automatic creation of attack pages. So this is where we focused on our research. So these are the contributions of our research. We present COSI attacks as a comprehensive category instead of calling them different names. And then we introduce the concept of attack classes to know which attack class works on which browsers and is based on which leak method. And then we identify a new cross-site leak method based on the PostMessage API. I explained this earlier. And then we present Basta-COSI. Italians must be familiar with the name Basta-COSI. And that's the name of our tool that can be used to automatically identify COSI attacks and build complex attack pages. So if you have a website you would like to check for COSI attacks, you can just run Basta-COSI against your website. So once we had the tool, we tested 4 standalone web applications and 500 top websites from the Alexa top sites, and we discovered COSI attacks on all of them. So let me explain to you the basic architecture of our tool. So the tool basically takes as input Selenium scripts to load different states in web browsers. And then after we have the Selenium scripts, we know how to load the states in the browsers. And then we want to collect different state dependent URLs. So we leverage a web app crawler in order to automatically identify different state dependent URLs. Then once we have the state dependent URLs of the application under test, we identify the attack vectors that are perfect or suiting for these state dependent URLs. And then we combine these identified attack vectors and automatically generate attack pages. And then these attack pages are like proof of concept to show that there is a cross-site COSI attack against the web application under test. So as I said, we conducted an evaluation using our tool on top websites. So we tested 4 standalone web applications such as HotCRP, GitLab, GitHub Enterprise, and OpenCart, and 58 websites from the Alexa top 150 sites. Since we deal with states, we focused only on those top websites having the account creation feature. The result was that we found at least one COSI attack on all the tested sites. We responsibly disclosed the identified vulnerabilities, and most of them were confirmed and some are already fixed, and we even received bug bounties for our report. So let me explain to you some of the most interesting ones vulnerabilities that we identified. So in hotcrp.com, which is used by most of the top security conferences for anonymous reviewing system, we identified that an attacker can identify the anonymous reviewers of any paper. And then in blogger.com, which is owned by Google, we identified that it is possible for an attacker to identify the author of an anonymous blog article. Then in Google Drive, it is possible to know whether the victim is the owner of a sensitive file that was uploaded to Google Drive. And then in Pornhub, it was possible to know if the user, the victim, is the owner of a specific porn channel. This can be a very sensitive information for some people. And then in websites such as IMDb, Imgur, and LinkedIn, we noticed that an attacker can track users by abusing COSI attacks across different browsers and across different devices. This is because the website in which they are logged in, that is IMDb, LinkedIn, and Imgur, are actually leaking their identity to other websites. And just to clarify this, these attacks work even if you use like anonymization services such as Tor, because these are like browser leaks. And then in GitHub and GitLab, it was possible for the malicious party to identify the roles of the victim on private repos. So let's say there is a private GitHub repository with a very sensitive hacking tool. These nation states can actually determine who actually worked on those tools and who has access to those repositories. So all these experiments were performed in a very responsible manner using the accounts that we controlled. So how can we defend from COSI attacks? So there are two types of defenses. One is the website-based defense that the website can actually use to defend against these attacks. So the first type should be famous for people working in the web security domain, that is same-site cookies. So same-site cookies automatically prevent the sending of cookies in a third-party context. So we saw that the malicious site is sending requests to foo.hotcrp.com, and it is actually when this happens, the cookies are automatically sent with these requests. So basically, same-site cookies are a way to prevent the automatic sending of these cookies. And then there are other header-based defenses such as cross-origin resource policy, fetch metadata, and cross-origin opener policy. You can read more about them in their documentation to understand more of how these can be implemented. Then there are browser-based defenses that can be used by users who use the browse on the web to defend against COSI attacks. So one of the defense is to enforce the default same-site policy. Most top browsers are actually moving in this direction, and some of them have already implemented this protection. The Tor browser, interestingly, when we tested, it behaved as if it had the default same-site protection, that is not sending cookies in the third-party context. However, during our experiments, we noticed that this does not prevent window-based attacks such as the post-message attack that we explained. And there is also this other attack using the frame count. So we actually responsibly reported this to Tor, and they actually took our report seriously, and they are actually planning to fix this. So to conclude my talk, we present different COSI attacks as a comprehensive category, introduced the concept of COSI attack classes. We identified a new cross-site leak based on the post-message API. We present Basta-COSI, a tool to automatically identify COSI attacks. And then we test different standalone applications and top websites and identify COSI attacks on each of them. So the technical details of our work are actually available in archive. So you can click this link to actually get more details. So if you have any questions, please let me know.
Hello, my friend. Do you hear me?
Yeah, I can hear you. Can you hear me?
Yeah, perfect. Cheers from Italy. I was in India.
It's fine. I just got married 2 weeks ago, so
yeah. You told me I was to get married with a lockdown.
Yeah, it was challenging, but also it was fun because usually in India there are like 1,000 people attending the wedding. Because of lockdown, it came down to like 50, so it was less challenging. It's okay.
You will have a chance to party.
Yeah.
Hey, cool. So thanks for submitting to our conference, and I hope you enjoyed what you've done so far. So we had a lot of questions coming up. I can count at least 5 of them. So the first one here I can read is about that yeah, you defined a new term if you want. I mean, all these different vulnerabilities that were unclassified before, now they go under the same category that you define as COSI. So the question is if you had any feedback from OWASP or other standardization community in trying to adopt such new category, for example, in to do when you do vulnerability disclosure or that kind of things, basically.
So this is actually a good question. So, but if you think in a critical way, what happened was there are already a lot of different names for these attacks. And although we systemized it, we also introduced a new name. So it's like we added a bit of more mess, right? So when we actually observed during the time this research was conducted, there was already an active discussion on how to call these attacks, to bring under a common umbrella and everything.
Mhm.
And Google was actually taking a lot of effort in doing this. And finally, the term that was actually, after a lot of surveys and everything, the term that they agreed to call these kind of attacks was excess leaks. And recently, they even started a website called excessleaks.com, where they
Okay.
actually clarify the different ways to perform them. So excess leaks became like the most the common terminology that can be used to call these attacks. So I'm happy in a way that I didn't contribute to a new name and then people had to learn this new name, but the community adapted to the name which was mostly familiar with among a lot of people. So yeah.
Well, it's a great recognition when you do research to see that what you do actually has an effect in some form, right? So good stuff. Okay, great. I will maybe discuss this later on with Michele and Giuseppe that come after your talk, and they're also working in web security domain, so I want to hear their feedback on this. But let's move forward with the next question, which there was someone that was I didn't really understood the way you can automatically map the return code to the different status of application, as you show in the slide. No, if a returns code is, for example, 200, then it means that the user is logged into the web application and possibly assigned to review a paper, right? If it's 4.3, it doesn't have it's not granted to review a paper. So do you need to have access to the web application under test, like to be able, for example, to load the application source code and so on, or can you do a black box testing of the application to drive this mapping?
Yeah, sure. So it is possible to actually do both. In fact, we did both approaches. We tested these 4 standalone applications and then a lot of Alexa sites. And these top websites, their source code is actually not available. So we used a black box approach for these top sites. We created accounts in them and we crawled the application and we fetched a lot of these state-dependent URLs. And then we tried to access these URLs from different states and saw whether they are returning different responses or not.
Okay.
Yeah. And then for the white box approach, like HotCRP, it's actually an open source application. So we actually identified, because by crawling the application, we did not find those, because we wanted to know whether we can de-anonymize reviewers. And through a black box approach, our automatic crawler did not find a URL that can actually do this. Then we actually checked the source code to see whether there exists such URLs, and we identified the URL that actually showed in the paper. And then we actually, through a white box way, we identified that URL. So an approach that mixes both styles is actually better for this.
Yeah, for sure. You have a larger, testing environment basically. That also bind also to the next question, which is how you select the application. I mean, you mentioned that you select the top Alexa application. That's a common technique when you do research, select top 10, top 100, whatever. So did you just pick up the top 100, whatever, or did you go for those one? I don't know, if you can elaborate on that aspect.
Sure. Yeah. So this research was done mostly from academic point of view, but then we also wanted to have an impact in the among people working on web security, but who are not very much linked to the academic side. So that's why we chose applications in which there are sensitive states. For example, hotcrp.com, de-anonymizing the reviewer is interesting for the academic security side community, and then knowing whether someone wrote an anonymous blog is interesting for the general community. And then we wanted to show that these attacks exist, or these vulnerabilities exist on top websites. So to do a systematic research, we chose the top 150 sites. And as I said, it's a bit time consuming, in the sense we have to create accounts in these sites, multiple accounts, because we want to see whether one user can infer another user's details, and then create different states. And then, as I said, we use an automatic tool, so we had to write Selenium scripts of these tools and then run the crawler. So it took a lot of effort. This is why we could only test 150 sites.
Yeah, for sure.
So
Yeah, understand. Yeah, that's also bind to the next question again. So you use Selenium basically to test the application. In this case, do you find a way? Do you think it would be possible to automatically patch an application to make actually the attack more difficult? So suppose the application use different return codes. You decide actually to merge this return code, so you just use a subset of this return code. Is there a way to automatically patch this application, or I
yeah,
don't know?
so there are like two different types of defenses, as I showed. Like the web browsers can take some steps, and the web applications can take some steps. So this is what the hot CRP application when we actually reported to them. They actually decided to standardize their response codes, like so that it always returns a 200 with the same type of response body. So it's not possible to actually infer through side channels, like what was the response, because it's always a 200. So it is possible to implement these kind of defenses, but then there is always like a URL that you did not patch or something. So when you try to like patch the application itself, it becomes more challenging. This is the reason why like same site cookies is actually being pushed by Google, because it is like one of the defense that, as you can imagine, it can actually break a lot of applications, but still Google decided to actually and a lot of other top browsers too decided to make it default. It's because like it makes these attacks very difficult. So both sides are actually, it's possible to actually kind of like in an automatic way reduce the impact of these kind of attacks.
Yeah, maybe left for future work. I mean, it's not as easy, this
Yeah,
automatic patching.
yeah, automatic.
Then we have someone, actually, this one we have name. Okay, we have so many questions. So I will go, I guess, for two more because we're already out of time here. So Jennifer is asking, isn't CSP supposed to mitigate this category of attacks? And if it's not the case, do you think it should be extended to cover COSI?
So like if you check the paper, if you will know that one of the side channels is basically CSP. So a security like a security feature that was actually used, that is actually meant to protect the application, is kind of can be used as a side channel to leak, perform this attack. So I mean, there are actually preventive measures, browser-based preventive measures like CSP, which is actually, I showed in the defense section. There are different headers that are actually available to mitigate these attacks. But I would actually agree to this, like making it like, instead of telling different headers for different responses, making it kind of like part of, let's say, CSP, so that it can actually be used to prevent these kind of attacks, is kind of like a sensible way. So yeah, the community is actually moving in that direction. But CSP has its own problems. Like many people are not willing to adopt it because of a lot of issues. So there are also different challenges. So if we go through the CSP approach.
Okay, thank you. And then we have Giovanni that says, thank you for the talk. Great. Would you mind clarify how a post message is fired when visiting a targeted SD URL?
Yeah. So there are like post messages that can be sent to specific domains. So let's say your page wants to send a message to your parent window. You can verify the origin and send that message. However, if there are ads on your page, ads are shown on different pages, right? So they cannot send a targeted message. So what they do is like they broadcast the message so that like whichever page opened them receives that message. So when you send a broadcast post message, or if the SD URL returns an HTML page that broadcasts a message, then it can be received by the attack page if it just opens it in a new window. So this is actually the broadcast feature in post message that can be abused. And in Google blogger of Google, this was the problem. Like the ad was actually broadcasting a message, and through this we were able to infer the state. So it's the broadcast message feature.
Okay, thank you. I would say to conclude with the last question. So there is someone asking if this Basta-COSI tool can be downloaded. I mean, if you are planning to release it or you are still working on that. So if you can elaborate on this tool.
Yeah, so this was actually developed as part of a larger open source project on testing applications. So a minified version of this tool is available as part of this project called Elastest. So it is already available there, open source. But as I said, it's for large type of testing. Like it includes functionality testing and normal cross-browser testing and everything. So if you're interested, you can check from there. Otherwise, just ping me in private and I can send you the full version. Yeah.
Okay, great. So do you have other comments? Do you have anything to say to our audience, or you happy with that? Or
yeah, like I would like to congratulate the organizers because we had so many challenges extending the deadlines and a pandemic. But in the end, I'm really happy that everything went well today, and there is a lot of participation. So I'm happy to see this.
Yeah, I will give some numbers in the closing after the next talk about how many people participate, and we're actually pretty happy. So if you will be online, you can attend the closing session. So thanks a lot for being with us, and I hope to see you again at some conference in person when we have a chance to travel. Thank you, and see you soon.
Thank you.